I just finished editing this fantastic interview with Dr. Ronald Mallett, Professor Emeritus of Physics at the University of Connecticut. This episode of Math Science History is all about exploring one of physics' most daring frontiers, time travel. Dr. Mallett has spent a lifetime investigating whether light itself can twist space-time enough to form loops in time. In this episode, we trace the personal moment that set him on his path and unpack the relativity behind traveling to the future and the past. So let's step into the lab and maybe, just maybe, outside the clock. Dr. Ronald L. Mallett, a theoretical physicist who spent decades studying Einstein's equations, takes us on an extraordinary journey from the spark that lit his obsession with time travel as a child in the Bronx to his revolutionary idea that light itself could twist space and time into a loop. In this episode, he unpacks the science of relativity in a way that is both mind-bending and accessible, and reveals how time really behaves under speed and gravity, and shares the personal and philosophical drive behind his research. From wormholes to frame dragging, from heartbreak to hope, this conversation asks, can imagination and mathematics really take us back to the moments we've lost? As Professor Emeritus of Physics at the University of Connecticut, Dr. Mallett specializes in Einstein's general theory of relativity and has published numerous papers on black holes and relativistic cosmology in professional journals. Professor Mallett's breakthrough research on time travel has been featured extensively in the media around the world, including print media such as New Scientist, Boston Globe, the Hartford Courant, Rolling Stone magazine, the Wall Street Journal, and broadcast media such as NPR's This American Life, the History Channel, the National Geographic Channel, the Science Channel, CNN, and a number of podcasts, including mine. Yay! Mallett has also been featured in major BBC documentary, The World's First Time Machine, and appeared in a feature-length Canadian documentary called How to Build a Time Machine, which won Best Documentary at the 2017 New York City Sci-Fi Film Festival, and both documentaries are available on Amazon Prime. Professor Mallett's published memoir, Time Traveler, a scientist's personal mission to make time travel a reality, has been translated into Korean, Chinese, and Japanese, and the memoir is currently in discussion to become a major motion picture. So without further ado, my listeners, enjoy this interview that I have with Dr. Mallett on his book, on his theories, and the reality of time travel. Dr. Mallett, thank you so much for joining us here at Math Science History. We're very grateful for your time.
Well, thank you for having me on.
We're going to be discussing your theories and work on time travel. And for the record, I've read your book multiple times.
Oh, wow.
I'm a big
Thank
fan.
you.
For my listeners who are meeting you for the first time, could you share how your father's passing set you on this lifelong path toward knowing that physics was the key to understanding time travel?
Yeah, I'll be happy to. I grew up in the Bronx, New York, and I was the oldest of four children. And my father, by the way, he served in the Second World War as a battlefield medic, but he decided to go into electronics on the GI Bill after he came out. He was a television repairman, and he was very, very good at his job. I mean, a lot of people who were younger, but people who are older will recognize the name Walter Matthau. My father actually fixed his television set at one time. Yeah, and I have an autographed picture of that. But the thing is that for me, the sun rose and set on him. He spent a lot of time with me. He would do things like give me toys like a gyroscope, crystal radio set. I mean, things like that really entertained me. And he would explain things to me. And I think he was interested in me eventually going into the business with him because he began showing me things behind the television set. He looked healthy. He looked strong. He looked robust. What we didn't know as children is that he had a weak heart. and he died suddenly of a massive heart attack. And to say I was devastated is actually an understatement. I mean, I went from being a really happy kid to being a very depressed kid. But among the gifts that he left me was a love of reading. I should mention he was only 33 years old when he died. I was 10 years old. And that was the first time I faced death. And it was incomprehensible. It was like Superman had died. And the thing is that about a year after he died, when I was around 11, I came across a Classics Illustrated version of what it was called The Time Machine by H.G. Wells. This is a copy of it.
Wow.
And the thing is that I read in it on the first page, it said that scientific people know very well that time is just a kind of space, and we can move forward and backward in time just as we can in space. And when I read that, I thought, if we can move forward and backward in time, maybe I could go back into the past and see him again and tell him what was going to happen, maybe change things. So my mother had kept his television and radio parts, and I used the cover of the magazine to try to put something jerry-rigged together. And of course, when I plugged it in, nothing happened, which was probably just as well, probably would have burnt the house down. But the thing is that I was disappointed, but not discouraged. I thought, it said scientific people know very well. So I knew science was going to have to play a role, but I didn't know what that meant. But as I said, I love to read. In fact, I love reading more than eating. I mean, literally, I would spend money that my mother gave us for getting lunches on going to the Salvation Army and getting books and things like that. And one time I went in and I saw this paperback, and it had a picture of Einstein on the cover. Now, I knew Einstein was this great genius. I didn't know what he did, but I knew he was this great genius. And next to him was an hourglass. So I knew that maybe this meant that Einstein had something to do with time. And maybe that might relate to, time machines. So what I did was I got the book. I was about 12. It's a popularization, but I couldn't really get the details. I just didn't have the background. But I did pick up the essence of what it said. It said that Einstein said that unlike the theories of Newton, who had said that nothing can change time, Einstein said there are ways you can alter time. So I thought if I could understand what Einstein meant by that, altering time, then maybe that would lead me to seeing whether or not a time machine could be built. So Einstein became my second passion. And that was the beginning. I knew I was going to have to go to college eventually, but that wasn't. And I should mention that after my father died, we went from doing well to poverty. It was hard. This was in the 50s. And my mother, she was African American, and it was hard for her to get any kind of a job. And it was only the most menial jobs that she could get. And fortunately for us, that we had the subsidies from the GI Bill and things like that helped us, going. But what I did was follow father's footsteps. He had gone into the military, and I went into the Air Force after high school. And eventually I used the GI Bill to go to Penn State University. And that's where I got my bachelor's, master's, and PhD in physics. I should mention, though, that remember, once again, this was in the 50s when he died. And I should mention there's an interesting coincidence to me that's always kind of haunted me a little bit. My father died in May of 1955. Einstein died in April of 1955. So they died just a month apart from each other. And I can remember even before my father died, seeing in the New York Times a picture of Einstein and saying, talking about his death. And the very next month, my father had passed away. But in any case, I knew that people were worried about me. Now, this was science fiction was not that big a thing as it is now. And I thought that if I told people that I wanted to build a time machine, they might not think that. They might say there's something wrong with this kid, So I actually kept it a secret. I didn't mention it at all to people. And eventually, when I went into physics, I decided I was going to have to use a cover story. And the cover story I used was black holes. It turns out that black holes were a creation of Einstein's theories, and black holes can affect time. And the thing is that black holes were considered crazy, but normal crazy, whereas time travel was crazy. So I thought, well, if I studied black holes, I could make that as my career. And at the same time, I would be studying about, Einstein's theories about time and the possibility of time travel. So that's what I did. And eventually, I did make a breakthrough. I eventually became a faculty member at University of Connecticut. in the physics department. And eventually, due to my work in black holes, I eventually got the tenure and became a full professor. And then the nice thing about tenure, and I always say that's important, because it allows you to go a little bit offbeat, okay? And you're protected by doing that. And so after I was able to become a full professor and reach the top of the academic ladder, I decided I could come out of the time travel closet, so to speak. And that's when I actually made my breakthrough. And that was at the beginning of this century. But the core of my work is Einstein. And it's based on that. And we can go into that. But that's the beginning for me. It was the death of my father that led me into this.
Mm.
And eventually I did make a breakthrough.
Your father was a tremendous inspiration in your life. That's
Yes.
wonderful.
Yes.
And as a quick side note, I'm just going to share this really quick. Walter Matthau went on to play the role of Albert Einstein in the movie IQ with Meg
Yes.
Ryan.
Yeah, in fact, yes, I saw that movie and I thought about that. In fact, I kept a picture from that, because I thought, isn't that interesting how that related? I mean, that came
Yeah, it
around.
all it all it's like a
Yeah.
closed time-like loop. It
y-
all connects.
Yeah. Thanks for, mentioning that, Gabrielle, because that was something that I thought about at the time.
This is a very broad question, but what is time and what is the science behind time travel? Because that's what is so inspiring about your work. You make it scientific and not just something in our imaginations.
Oh, thank you. Yeah. Well, the way I think of time, if I was to give a quick definition, it's the persistence of existence. And what do I mean by that? Is the thing is that it has to do with duration. And I'll use an example that was actually used in the time machine. Suppose that you have a cube, okay? A cube has length, width, and breadth. Those are three dimensions. But if the cube didn't have an existence, if it didn't endure, then it wouldn't exist. So it has to have a fourth dimension, the dimension of time. It has to endure. So to me, that's what I mean by the persistence of existence. Something has to persist in order to exist. And that's what time is. So time is the persistence of existence. That's the fourth dimension. That's what I think of it as. But now, as far as the scientific basis of time travel, that is, Einstein developed two theories. The first theory was developed in 1905. It's called the special theory of relativity. And to put that in a nutshell, what Einstein said is that time is affected by speed. The faster we move, the more time slows down. Time for a moving clock slows down. Now, when I talk about a clock slowing down, I don't mean just simply mechanical clocks. Your heart is a clock, okay? It beats at a certain rhythm. Now, when you're going down the highway traveling at 65 or 70 miles an hour, you don't feel that. It's people who see you zooming by. It's the same thing with this. If you're traveling very high speeds, you won't feel time slowing down. You won't feel your heart rate changing. But people who are watching you would actually see your heart rate slow down, your metabolism slow down. In other words, time would actually slow down. For them, time is moving along at a normal rate, but they would see time for you as slowing down. Okay. And so now you might say, has this been shown? Not only has it been shown, there was actually experiments on both the and uh, macroscopic and microscopic. There's a device that's in CERN, Switzerland, called the Large Hadron Collider. What it does is speeds up subatomic particles. Okay, some of these particles only live for a very short period of time, and then they just simply disappear. They disintegrate. Okay, now what they find is that when they speed these subatomic particles up close to the speed of light, they can get these particles to live 10, 20, 30 times longer than they normally would. What that means is that their internal clock is slowing down, just exactly as Einstein predicted. But not only that, we've seen it on a macroscopic level. This is something that people aren't generally aware of. Back in the 1970s, an experiment was done in which they took two atomic clocks. One of the atomic clocks they kept at rest at the Naval Observatory. The other atomic clock they put on an ordinary passenger jet and flew it around the world, close to the speed of sound. When they brought it back, they found that the clock on the passenger jet had actually slowed down compared to the clock at rest at the Naval Observatory. This means that the scientists on board, their heart rate, their metabolism has slowed down. Now, you might say, how come this wasn't in the New York Times and everything? Well, the effect is so small, it can only be measured with atomic clocks, okay? The thing is that it depends on speed. This effect happens at any speed, by the way. But the closer you get to the speed of light, the more dramatic it becomes. Okay. So if we were had rockets that can go close to the speed of light, and we are developing rockets, that possibility, then we would see the effect in much more dramatic way. For instance, an astronaut who's traveling, let's say, out to a distant star that's about, let's say, 20 light years away from us, okay, from the people here on the earth, if they were watching that astronaut, it would seem to them as though it took 20 years for the astronaut to go out and 20 years for the astronaut to come back if they were going close to the speed of light. However, for the astronaut, time is slowing down. So when they come back, even though for the people on Earth, it would seem like it took them 40 years, for the astronaut, it could seem like it only took 10 years. So then the astronaut came back, the astronaut would only be 10 years older, whereas everyone else here on the earth would be 40 years older. Now, it's time travel. Time travel is when you have the person get into some device and they come out in the future and they haven't aged very much, but everyone else has. So, that, and as I said, we've seen the baby steps of that with the experiment that was done at the Naval Observatory. So, that is real. Time travel to the future is real. And as I said, it's based on Einstein's special theory of relativity. So once again, Einstein's special theory of relativity says that time slows down. But now, how about going back to the past? Well, no matter how fast you go, you can't go back to the past. There is a speed limit. That's the speed of light. So you can get close to the speed of light, but you can't get past it. Incidentally, people thought that there was a speed limit on sound, and we broke the sound barrier. It turns out that the speed of light is a whole different thing. It's actually built into the fundamental structure of the universe. There's a very famous equation called E equals mc squared, which every child hears about. It just simply relates energy to matter. It says that if I have a certain amount of matter, then it's equivalent to a certain amount of energy. That equation works because of the speed limit. Okay. Now, you might say, "Well, how is that related to that?" Well, suppose that I want to speed something up. Essentially, I want to push something and get it to go faster. Okay. To do that, I have to give it some energy. Okay. Now, Einstein's equation, people sometimes think of Einstein's equation in terms of if I have a little bit of matter, I get an enormous amount of energy. That's what E equals mc squared says. But the equation can also be read in reverse. That is to say, if I have a certain amount of energy, that can give me a certain amount of matter. So when I try to speed something up, okay, some of that energy actually goes into the mass of the object that I'm speeding. That means that object becomes harder, becomes more massive. And so that means that if I want to get it to go even faster, I've got to give it more energy. But when I give it more energy, that energy goes into making the object even heavier.
Wow.
So eventually, if I try to get that object to go at the speed of light, I would have to give it almost an infinite amount of energy in order to get it to do that. And when you say that you need an infinite amount of energy, that's the same thing as saying you can't do it. So because of E equals mc squared, literally that puts the limit on why we can't just simply accelerate something beyond the speed of light. So it's built in. Okay, that's important to realize. So it's not just simply a barrier. It's part of the fundamental laws of physics. Okay. So how can we go back into the past? And well, it turns out that Einstein developed a second theory that leads to the possibility of going back. His second theory was called the general theory of relativity. And it took him 10 years to develop that. The first theory was developed in 1905. It was 1915 that he came out with the second. You might say, why? Well, he had to develop a whole new mathematical set of equations, okay, extremely complicated set. The mathematics is called tensor calculus. But the point is that what is that new theory that he had to develop? Well, it has to do with gravity. Now, let's back up here. What do I mean by that? Well, when Einstein developed his special theory of relativity, he tried to apply it to everything. And it turned out that the one thing he wasn't able to get it to work was gravity. Now, why was that a problem? Well, let's go back to how the relationship between us, gravity, and the sun. We know that we're 93 million miles away from the sun. Okay,
Mhm.
and the Earth, the gravitational force of the sun keeps us in orbit around. Now, suppose that some cosmic catastrophe were to destroy the sun. What would we see? And I use that in a very specific way. What would we see? Well, we know that it takes 8 minutes for
Thanks.
light to get from the sun to the earth. So that means that if the sun were destroyed, we would not see that for a full 8 minutes. In other words, we would actually see the sun still sitting there in the sky. But if the sun was destroyed, gravity, according to Newton, would shut down immediately. So we would have the following weird consequence. We would actually still see the sun setting out in the sky, but since the sun isn't there anymore, really, gravity is shut down, we would be hurtling off in space. So that's a contradiction. We would be hurtling off in space, but we would still see the sun sitting out there. Einstein said, wait a minute, that implies that gravity can travel faster than the speed of light. Because that if gravity shuts down, that means that the effect of gravity could get to us before light could get to us. And so Einstein said that means that there's something wrong with gravity. He had to put a limit on why gravity can't travel faster than the speed of light, according to his theory, his special theory.
Okay.
So he had to develop a whole new theory of gravity.
Wow.
And this whole new theory of gravity said that gravity isn't really a force, it's a property of space. What do I mean by that? Well, imagine that I have, let's say, a rubber sheet, let's say a small trampoline, okay? And let's suppose that I take a bowling ball and I put it on the rubber sheet, okay? What does it do? It curves the rubber sheet, okay? Now, suppose I take a marble and I put it on the rubber sheet. Well, when I put the marble on the rubber sheet, because the bowling ball is curving the rubber sheet, the marble's going to roll down towards the bowling ball, okay?
Yeah.
Now, suppose that the rubber sheet is there, but it's transparent. So the only thing you see is the bowling ball and the marble, okay? So when I release the marble, it moves towards the bowling ball, but now you can't see the rubber sheet. So somehow you would think that the bowling ball is exerting some force on the marble, pulling the marble towards it. But you know that's not what's really happening. Einstein said that's what's happening in space. The sun is like the bowling ball. The sun is actually bending, warping space around it. The earth is merely moving along that warp, but we can't see the bending of space. So we think that the sun is actually directly pulling on the earth. It's not. So the thing is that what I can do is I can actually show in a sort of an experiment that if I have the bowling ball on the rubber sheet and I have the marble, if I give the marble a little bit of a sideways motion, I can get the marble to orbit the bowling ball. That's what's happening to the earth. When the solar system was formed, the earth had a little bit of a sideways motion. So even though the sun was warping the space, the earth was moving along that curved space like a skater on a roller derby track, okay? So that's what gravity is. Gravity is actually the bending of empty space by a massive object. Now that's important because now let's come back to the bowling ball and the marble. Suppose that I pull the bowling ball suddenly off the rubber sheet. What happens? The rubber sheet vibrates a little bit when I pull it off, okay? What happens when the sun is destroyed? When the sun is destroyed, it's like it being pulled out of space. And so space starts vibrating a little bit. Now, remember, I said that gravity is the bending of space. Those vibrations of space are what we call gravity waves. Gravity waves are actually the bending of the oscillations of space. So what happens is that if you calculate how long it takes for those vibrations from space to reach us, it takes 8 minutes. Okay. So what that means is that what Einstein said is that if it's any kind of a consolation, if the sun was destroyed, it would take 8 minutes for the gravitational effect to reach us, as well as 8 minutes for the light to reach us. So when the sun is destroyed, the effect of that would still be there. Okay. until it reaches us 8 minutes later. So whenever the light goes out, the gravitational goes out, and we go off into space. Okay, so that's what's his new theory, is that gravity is actually the bending, the warping of space. Now, this affects time as well. In Einstein's theory, in fact, you hear sometimes the phrase space-time. Whatever you do to space also affects time. So that means the bending of space shows up as the bending of time. Now, what does the bending of time mean? That shows up with clocks being affected by gravity, so that a gravitational force will actually cause clocks to slow down. Now, you might say, has this been shown? Not only has it been shown, it's part of our everyday life. I know that I have in my car, and you probably do in yours, a GPS system. The GPS system works because of Einstein's theory. Now, how did that come about? Well, it turns out that the way in which the GPS system works is the following. In your car, the unit has a clock associated with it. What happens is that the satellites above the Earth, there's a very simple relationship in physics between distance, time, and speed. If you know any two of those, you can compute the other. So if I know the time the signal was sent from the satellite, the time it reaches my unit, and I know the speed of the signal, I can compute distance. When they did that, okay, they were getting incorrect distances. Why? Because they were assuming that the clock on board the satellites were running at exactly the same rate as the clock in your unit. According to Newton, nothing can affect time. According to Einstein, however, the clock in your car, because gravity is stronger at the surface of the Earth, that clock is actually running a little slower than the clocks on board the satellite. They're running at different rates because they're at different places in the gravitational field. You have to use computers to take that into account. And so that is what's done. So anytime I use my GPS system, I always give a silent nod to Einstein, because without his theory, we wouldn't have GPS. So it really has practical consequences. So time is affected by gravity. But now it turns out that because of that, there's other effects that are associated with that. Suppose that we have an object like a rotating black hole. Now, I should mention what a black hole is. I'm sure most listeners may know, but a black hole really isn't as mysterious as it seems. It's simply an effect of collapsing gravity of an object. The sun is a good example. The way in which our sun operates is that there's a balance, an interesting energy balance, essentially a ball of hydrogen gas, simplifying things. But what happens is that the gravitational pull in this gas is pulling the hydrogen atoms together. And then when they smash into each other, they form helium. There's a little bit of a difference in mass from the resulting helium from the hydrogen. That little bit of mass that's there is converted into energy from E = mc squared. And that's where we get the energy from our sun. So the energy from our sun is due to the result of the collision of the hydrogen gas forming helium. Now, eventually what's going to happen is that fuel is going to begin to get used up, okay? And what's going to happen is that things are going to be able to start shutting down. The gravitational force pulls inward. The heat from the gas is pushed outward. Eventually that internal energy is going to get shut down. And so that means the gravitational force is going to start dominating. That means the star shrinks and collapses. The gravitational force around it becomes greater. Eventually, the gravitational force becomes so great that the light that tries to escape, we don't normally think of light as having weight, but the light that tries to escape, the light gets pulled back. So if you're standing outside the star and all the light that tries to get out of the star gets pulled back to the star, what do you see? Nothing. That's what a black hole is. A black hole is just simply a star, a collapsed star that has collapsed to a point that all the light that tries to escape is pulled back. And so all we see is a black hole. It would actually look more like a black sphere in space. It turns out that, remember that time is affected by gravity. So that means that if you were going close to a black hole, because gravity is becoming greater, time is slowing down more and more and more. If you got close enough to a black hole, time would almost come to a stop. It turns out that not only will that happen, if a black hole is rotating, then not only will time get pulled back, but time itself will get twisted. The way of thinking about that is the fact that suppose that I had a strip of paper right now, and on the strip of paper, I drew a straight line. At the bottom of the strip of paper, let's call that the past. At the middle of the strip of paper is the present, and at the top of the line is the future. Now, remember this, I've drawn this timeline on a strip of paper. So the strip of paper represents space, and the timeline is in space. Now, what happens is that the rotating black hole will actually cause space itself to get twisted, okay? Think of a way I use an analogy of this is that think of you have a cup of coffee, and think of the coffee as being like empty space. Okay. And think of your spoon as being like the rotating black hole. So what happens if I take the coffee and I stir it? The coffee starts swirling around. Yeah. That's what a rotating black hole is doing to empty space. It's causing space to come swirling around. That means that, remember, space and time are linked to each other. So that strip of paper that's normally going from straight line from the past, present, and future, that will get twisted into a loop. So imagine I take that strip of paper and twist it into a loop. I could go from the past to the present to the future, but I've made that strip of paper into a loop. So I could go from the future to where? Back to the past. So by twisting space enough, I can twist time into a loop. And along that loop in time, I can go back to the past. So that means that for a rotating black hole, I could actually use that as a time machine to go back to the past. That's real. That's based on Einstein's theory. And we know black holes exist. In fact, the Nobel Prize was won just back in 2017 for the real discovery of black holes and gravitational waves, by the way. And so we do know that all of that is possible. But now that's out in space. Is it possible for us to have a mechanism that we could do here on the Earth? Well, that's where my work comes in.
Yes. We'll be right back after a quick word from my advertisers.
Because what I was interested in was that possibility. So I had spent my life studying black holes, and so I knew all of these things. And I should mention, I'm a theoretical physicist, I should mention. In physics, there's a big difference between experimental and physics and theoretical and experimental physics. Einstein, for example, was a theoretical physicist, okay? He didn't do experiments. What he did was he used equations to describe how the universe works. Experimental physicists actually use equipment to see that if this is the way the universe really works. My work involves solving Einstein's equations. And what I did was I wanted to know, is there a way that we could find a way of twisting time that was different from using a black hole? Well, it turns out there's an effect in Einstein's theory. In Newton's theory, the only thing that can create gravity is matter. The matter of the sun keeps us in orbit. The matter of the earth keeps us grounded, and so on. But in Einstein's theory, not only can matter create gravity, but light itself can create gravity. Even though light doesn't have mass, it can create gravity. Now, this is where my breakthrough came in. If gravity can affect time and light can create gravity, then light can affect time, okay? And what I did was I utilized that in the following way. There's a device, and it's a real device, it's called a ring laser. A ring laser is just simply a device that takes a laser beam and causes the laser beam to go into a loop, okay? You can do this by having the light beam go off mirrors, okay? Now, what I did was I solved Einstein's gravitational field equations for a ring laser. And what I found was that it can cause a twisting of space itself.
Mm-hmm.
And what I did found was is that if you cause that twisting of space to become great enough, then you could actually cause a twisting of time into a loop.
Wow.
So in effect, what you could do is create loops of time with a circulating beam of laser light. So this was essentially a laser generated time machine. And it's all based on Einstein's general theory of relativity. So that was my breakthrough, was to show that by using a circulating beam of laser light, mathematically, you could cause a twisting of space and then eventually a twisting of time, which could allow you to travel back into the past. Now, that's one thing to show it mathematically. It's another thing to do it experimentally. And that's the same thing that happened with Einstein's equation. Einstein's equation, for example, equals mc squared. That's something he came up with theoretically. But to create that from the mathematics to the experiment, that would probably have never happened if it hadn't been for the Second World War, because the cost of that was billions of dollars. The Manhattan Project is what led us to be able to go from Einstein's theoretical equation to the real possibility. It's the same thing with my work, okay? That's theoretically, I've shown that it's possible. The experiments, however, have yet to be done because of the cost of the experiments. And that's another story in itself altogether. I always feel that, it's funny. Here, we have been responsible for in this country, for major breakthroughs. But we seem always to do it in response to give you an example, atomic energy was developed in response to the Second World War. Sputnik is another example.
Yeah.
In 1950s, in 1957 is when the Russians sent a little satellite out in space. Prior to that, we weren't particularly interested in going into space. But as soon as we saw that little thing going around, we decided we got to get on the train here. And so we developed that. So it's always been this. And I always semi-joke that if the CIA tomorrow found out that North Korea was interested in time travel, I would probably have more money than I knew what to do with for my experiments. So, but that's just simply the way that it is. Okay. But that's where things stand right now.
So you created a model with Dr. Chandra Roy Choudhury. The machine, is that the Lotart?
No.
No.
Yeah, no. Well, the thing is that the theoretical device that I created that mathematically. Chandra, who's an expert in lasers, he became interested in proving my theory. Okay. So what we did, though, was for the purposes of giving people an illustration of what it would look like, what we did was to create a device that isn't a real working device. In fact, there's a number of documentaries that are out there that I've done. If people are interested, in fact, there's two major documentaries that are both available on Amazon Prime right now. One's called The World's First Time Machine. That was a BBC documentary. And then there's a Canadian documentary that came out more recently that's called How to Build a Time Machine. And as I said, both of those documentaries are there. There's a model that they see there. And people have asked me about that. That's actually not a working device. That's just simply something to illustrate what it might look like if we had the funding to actually create it. So it's not even really a prototype. It's just simply a toy model to show what it might look like if we did it. And then what you see is these beams of light that create a circulating beam, but that isn't a working device. As I said, that's just simply an illustration of what a device might look like if we had the funding to actually create the device.
Seen both documentaries. They're fantastic. I'm curious to know then, amidst the mathematical applications, you talk about frame dragging and how that's central to your theory.
Right.
And I'm really fascinated with this. Would you mind explaining this to my listeners
Sure.
and why
Yeah.
it's so important to the physics of time travel?
Yeah, thank you, Gabrielle. Well, in my work, for me, one of the ultimate goals was the time machine part. But leading up to that is this notion of frame dragging. What frame dragging means is the fact that, remember I said that this circulating beam of light, the circulating beam of light actually is causing a twisting of space analogous to what I was saying before. If you had a cup of coffee, in this case, the space is still like the cup of coffee, but the spoon is like the circulating beam of light. Okay. So whenever you turn the circulating beam of light on, you actually cause a stirring of empty space. And that's called frame dragging because you're dragging the frame of reference around when you turn the light beam on. So that's a twisting of space. So this twisting of space, and here's the thing that for me is important, is that to show that is necessary because you have to have the twisting of space before you can get the twisting of time. Okay. And mathematicians have a phrase that's called necessary and sufficient conditions. The necessary condition is having the circulating beam of light. The sufficient condition is having that beam of light intense enough to cause the time to become twisted as well. But now, why is this spin-off important? It turns out that the frame dragging of space is actually less expensive and is within our technological means. Why would that be important? Let's suppose that, I'll give you a good example of that. Suppose you're sitting in a bathtub and you want to get the bar of soap from one end of the tub to the other. Okay, what do? You push the bar of soap through the water and it goes to the other end of the tub. Now, suppose you want to get it there faster. Well, one way that you could do that is, in addition to just pushing it through, suppose you hit the water too. Then the soap now that's sitting in the water will be moved. But now, so in addition to pushing the water going through the water, it will be going with the water. So it will be going a lot faster. So how do we transfer information from one place to another? All the means that we have now, the standard means, is we transmit information through space. No matter what process you can think of, the information is transferred through space. Suppose that in addition to transferring information through space, we use space itself so that we push space. If we warp space so we could push space, information now would not only go through space, but it would go with space. So we get an extra boost. So imagine if you did that, you could transfer information much more rapidly by making it go with space as well as through space.
Wow.
Not only could that be, but that would even mean as far as transporting objects by warping space itself, we could actually get things to travel in space faster than they normally would just by going through space. All of that is at the level of what we could do now if the funding was possible. So that frame dragging effect that you're talking about is something that has practical implications at low energy levels that don't involve the direct thing of time travel as well. So I'm very pleased that you brought that up. So the frame dragging by light effect is necessary as the basis for the possibility of time travel, but it's separate, from it. In other words, it's a necessary condition, but it happens first, and then you have the time travel effect. So that is very important. Frame dragging is a necessary condition, and it's something that we could possibly prove without a huge expenditure
What
of
a lot of
energy.
money. Yeah.
Right.
Imagining that funding isn't a constraint, what would that look like to prove that?
Okay, well, the thing is that the simplest example, coming back once again, and I'm going to use this analogy with the cup of coffee. I talked about the twisting of space. Now, you can't see space, so you would actually say, how do I know that space is actually being twisted? Well, let's suppose we come back to the cup of coffee. Suppose that I drop a coffee bean into the coffee, and then I start stirring. What happens is the coffee will start dragging the coffee bean around. Okay, right? Now, in this experiment, what would be the analogy? Suppose I had a neutron. I did several calculations later, and you could actually do it with an electron. If you had the circulating light going through fiber optics, you could actually then use a subatomic particle like an electron. You don't have to use a neutron. So let's say I have a spinning particle. The main thing is I put a spinning particle in there. If you have a spinning particle, it has an axis of spin, okay? Just like the Earth has an axis. When I put it in there, as I use the circulating light beam to stir space, space will drag the spinning particle around. So what I would see is I wouldn't see the space itself starting to twist, but I would see all of a sudden when I turned on the circulating light beam, all of a sudden I would see that spinning particle, I would see its spin getting twisted. So
Wow.
its spin would be getting twisted because it's being dragged around by the empty space. That would be a direct and real engineering way of seeing that space is being twisted. Does that answer?
Yes, it does. There's a multitude of ways I'm sure we can accomplish something like that.
Oh, yeah.
So we'll find you a couple $1,000,000.
Well, people listening to your podcast who have deep pockets, that would be great.
That would be fantastic. I know that it was considered outlandish in your time early on for not bringing up that you wanted to create a time machine. What did you observe over the years that encouraged you to finally come out of the time machine closet?
Yeah. Well, the thing is that there were other physicists who were looking at these things who had high creds within the community.
Yeah.
One of them, for instance, who won the Nobel Prize, Kip Thorne is his name. And he was one of the people who had looked at these things that are called wormholes. Wormholes are like tunnels in space, okay? And what you might think of is if you had two black holes that were in different parts of space and you had a tunnel connected the two of them, okay? So you could go into the black hole this way and then come out of the other one. But what he found was that if you look at this mathematically, it turns out that there are ways that you can use the wormhole by using a twisting of the wormhole's mouth. You could actually set things up in such a way that when you send something in, when it comes out, it could actually see itself going in. Okay.
Wow.
So it could actually see the past. So that was time travel essentially to the past. So, and at Princeton, there's a man named Richard Gott, who's a theoretical physicist. And what he showed is that there's these masses, they're actually, you might say, strings that were formed from the Big Bang. They're just sort of strings in space. They're actually cosmic strings. These are different from the other type of strings in particle physics, but these cosmic strings, and what he said is that these cosmic strings are moving past each other. They could cause loops in space and loops in time, okay?
Wow.
So what I was beginning to see is that people who were respected in the community were actually talking about ideas that might be related to time travel. And then there was actually another physicist who's actually a mathematician. This actually happened very much earlier. His name is Gödel. He actually proved it's something called the indeterminacy equations in mathematics, okay? Equations of undecidability. Essentially what he was really, I don't want to completely cut up his theory, but essentially the essence was that you can't completely prove how complete a set of equations are within the set itself, okay? There's always something that's undecidable. You have to go outside that theory, sort of a meta theory, in order to prove the completeness of the theory before it. But one of the things is he was a colleague of Einstein, by the way, at the Institute for Advanced Study.
Dr. Kurt Gödel.
Yeah, that's right. That's Kurt. That's right. That's the famous Kurt Gödel. And the thing is that for Einstein's birthday, 70th birthday, what he did was to solve Einstein's equations, gravitational equations. He said, if you have a rotating universe, what he was able to show mathematically was that this rotating universe would cause loops in space, and these loops in space could lead to loops in time. And so he actually even states explicitly that within this rotating universe, it could be possible to travel back into the past. So for me, having people like Gödel saying, that Einstein's theory could lead to the possibility of time travel to the past, that boosted my confidence in that possibility. Now, there's still one other aspect that's associated with this, because now I feel comfortable, okay? And I feel on solid ground because of the fact that my work is based on Einstein's theory, and I have these other people that I can point to who have been looking at this. But one of the questions that still comes up doesn't have to do with the mathematics, but has to do with the possibility of paradoxes within the notion of time travel to the past. Time travel to the future there are no contradictions. There's no problem. You go to the future, everyone else is still stuck in the past, so you can't affect things. Okay, you just arrive in the future and see how things have changed while you were gone, so to speak. Suppose that you go back to the past and prevent your grandparents from meeting each other. Then your grandparents don't have your parents, and your parents don't have you because they don't exist. So if you don't exist, how did you go back to the past to prevent your grandparents from meeting each other? Okay, that's called the grandfather paradox, where you go. The most interesting example of that is in Back to the Future, where
Yes.
Marty McFly, you know, his mother is falling in love with him,
That's
rather
not
than with his
supposed to
future
happen.
father, and that's not supposed to happen. Okay, and so he starts to vanish. I mean, but that's the grandfather. Well, it turns out that physics itself has a way around this that has to do with the other pillar of physics. Modern physics is based on two major pillars. One is relativity, the other is quantum mechanics. And if you think relativity is strange, you haven't seen nothing yet
Yeah.
when you're dealing with quantum mechanics. Okay. And it turns out that quantum mechanics has its own. There was a physicist, Hugh Everett III, back in the 50s. What he wanted to do was to apply quantum mechanics to the universe as a whole, because he thought there were certain problems that were with the standard theory of quantum mechanics. Suppose that this afternoon you're trying to decide, you go to for lunch and you look at the menu and you see item A on the menu and you see item B on the menu. And suppose you decide on having item B. Okay. At that instant, it's Gabrielle who has chosen item A in another separate universe. That other universe is just as real as this universe, but there's two separate you. There's one that has chosen item B and one who's chosen item A. We now popularly call this the parallel universe idea. He originally called it the many world interpretation. And what it says essentially is that whatever you do, no matter what it is, its other possibility occurs as well. Now, there was a physicist at Oxford University named David Deutsch who looked at this possibility from a mathematical standpoint and applied it to time travel. And what he found was the following. Suppose that you travel back to the past. Okay. At the instant you travel back to the past, there's a split of the universe. You arrive in a parallel universe. In that universe, you prevent your grandparents from meeting each other. That's okay, because you weren't even born in that universe. You just now will find yourself in a strange universe in which you're in that universe, but you never occur in that universe. Okay. But remember, I said there was a split. That other universe you don't arrive in. In that other universe, since you don't arrive in it, your grandparents meet each other, have your parents, and your parents have you. The upshot of it is what he said is that you can travel back to the past, but the past you arrive in is not the past that you came from.
Okay.
So you don't create any paradoxes because of that.
Wow. Okay. That's a perfect workaround. That's
Yeah, and that's
amazing.
based on quantum mechanics. So that's one possibility. Now you might say, which is it? Well, the only way we're going to find out is once we do the experiments. But once we do the experiments, then we will actually know whether or not this occurred. But the main thing is that Einstein, the ultimate point is that Einstein's general theory of relativity does lead to the real possibility of time travel to the past, and it's now just going to be us to see how that plays out.
Let me ask you this then. I know the answer to this, but I would love for my listeners to hear this. What would be the real world applications of this mechanism, this machine working, and how could
Yeah.
it benefit society?
Right. Well, the first part is that, as I mentioned, we already talked about, the frame dragging part has obvious possible applications as far as communication and transportation is concerned. But the time travel portion for me is that, think about tsunamis, earthquakes, all these natural disasters that occur. Imagine if we could have, and COVID, for example, the pandemic, imagine if we could have advanced information about these things.
Yeah.
Okay. Wouldn't that be worth it? I mean, think of the millions and thousands of lives that we could save by that. What the possibility of time travel gives us a possibility of controlling our destiny in a way that we can't even begin to imagine. So just from that standpoint alone, it's worth looking at and looking at the possibility.
So, going back to the paradoxes, there's something that you bring up in the book, and I understand that we will know that time travel is real the day we create the time machine. Is that correct?
That's a very good point. The thing is that time travel, terrestrial time travel, has a limitation. That is to say that when we see the movies, and I should mention that I'm a big fan of time travel movies. Anytime there's a new time travel movie coming out, I'm going to be there to see it.
You and me both.
But I separate that from reality. Okay, to give a good example, Terminator is a good example. You know, you have Schwarzenegger all of a sudden appearing in the past. Okay, not really, because there's a device that created these loops. Okay, and before the device was turned on, there weren't loops in time. You turn the device on, and that's when they begin. It's like having your television set. You can't get something from your TV before you turn your television set on. Okay, that's called causality. The effect happens to happen, after the cause. What that means is that if I turned on the device today, these loops would start being created. And if I left it on, let's say 10 years, someone 10 years from now could travel back or send information back all the way back up to the time the machine was turned on. But they can't send it earlier than that because the device didn't exist earlier than that. So it actually answers a question that Stephen Hawking had brought up. Time travel to the past is possible. How come we're not inundated with time travel tourists? The answer to that question is that the machine hasn't been built yet that allows for that. Okay, so that's the real possibility. That's the real limitation. But does that mean that we couldn't get visitors from the future? Not necessarily. You might say, well, why not? Remember, this universe that we're living in, one of the things that physicists since the 90s is the fact that there are other solar systems than ours. There are other suns that have planets around them. Now, believe it or not, prior to the 90s, we didn't know that there were other planets that had their own other suns that had their own planets around them. These are called extrasolar planets. This is now a real scientific area of study. What is believed now is that there are probably conditions with some of these that have life. As a matter of fact, physicists like to give these things colorful names, that these extrasolar planets that probably could support life are called Goldilocks systems. That is to say that there's planets aren't too close, so they're not too hot, or they're too far away, so they're not too cold. They're just right, around their suns. And so the universe is probably teeming with life. Okay. Now, some of these planets may have developed life so that those civilizations are extremely advanced and may have created time machines or devices that have been turned on thousands of years ago. If we were to able to find these planets, we could actually use their time machines to visit our ancient past. Okay, so the thing is that it still has the same limitations, I should mention, but nevertheless, it is possible. But for us terrestrially, the next time that it's going to happen here terrestrially is when we create a time machine and turn it on.
That's fascinating. That's mind-bending. Well, the multiverse theory in and of itself is a mind bender. It's very exciting to hear because these things are possible.
Oh yeah, we live in a strange universe, but I think it's stranger than we can even believe to begin.
That's the
And it's
beauty.
real. Yeah,
And the foundations are all in math.
that's right. That's exactly right.
Back to funding. Building on top of this machine, if funding weren't a constraint, what would you commission tomorrow?
Well, tomorrow, what I would do is I would find Chandra and say, "Hey, look, we're going to be able to get back to work here." And I would say, first thing that we would want to do is to show that frame dragging
Mhm.
is that would be the very first thing, because as I said, the funding for that really is something that is not out of bounds. And it's the necessary condition. We were talking about mathematics. That's the necessary condition. We have to show that frame dragging is there.
Yeah.
Plus, it has its own immediate practical applications associated with it. So that would be the first thing that we would actually fund is just showing that frame dragging by circulating beam of light is real, not only theoretically possible, but it's actually practically possible. then we would go from there, because what you do is you learn at different steps. So what we would learn is what is necessary to do that. The other thing is that everything that I've done so far has not brought quantum mechanics directly into it. So I think that quantum mechanics is going to make going from the twisting of space to the twisting of time a lot easier than we think that it's going to be. Right now, the energy barrier in going just from twisting of space to the twisting of time is a huge energy barrier. And I mean, I have to agree with my scientific colleagues who say, the Mallett's theoretically been able to show this, but is it practical to do it? The frame dragging part, yeah, but going from the frame dragging to the time twisting, it seems like it needs galactic amounts of energy to do that. But that's where quantum mechanics comes in. It may be that barrier is much lower than we think. This is what happened with, the atomic energy project. It seemed like it was going to be much harder to do than it turned out to do, but that was because of quantum mechanics. So that's something that we haven't even begun to explore yet. But that would be the first thing we're looking at, is frame dragging by light.
Okay. As far as your research and how it has evolved over time, I'm curious to know where your current research sits.
Okay, that's a good question. But now you opened it up in a different direction, because
Oh,
my current interest right now, which hopes that we'll come back to it, is the fact that you mentioned my book. By the way, I hope that people will be interested. The book is both a memoir and a science book. Thank you, Time Traveler, which is available from Amazon, by the way. There's a real possibility that that's going to be made into a feature film,
oh
I should
my
mention.
God.
I actually have a producer that is interested in doing this. And it turns out that there's other producers who are really excited about the book, mainly because, from the Hollywood standpoint, they're interested not just the science part, but of course the father-son story is something that they're really interested in, and what's driven me, because I had a lot of obstacles in my life. Being African American has been interesting, to use that general phrase. But the thing is that is what I've been interested in currently. Now, from two different levels. One, because I would, for me, it's almost as close as I may get while I'm alive of actually seeing my father alive again, because it would bring him to the big screen and I would be able to actually see this representation of him. So for me, that's almost the same. Okay. That's one aspect of it. But when things go to a feature film level, that brings an awareness to a larger audience. Maybe someone like an Elon Musk now, says, hey, wait a minute, this guy's work is based on Einstein. Maybe he's not crazy. Maybe let's take a look at what he's doing. But in any case, it brings it to a larger group. And so the funding may come from indirectly because of that greater exposure at that level. So that's, you might say, one of the things that I'm really interested in right now is trying to help shepherd this thing and give encouragement to my producer and my agent to have this made into a feature film.
That would be everything.
Yeah, exactly.
So I really hope that this one goes through. I know we need to wrap up. I have a final question.
Sure.
Your journey feels both scientific and deeply human. As my father's daughter, I can relate to your journey. And I'm wondering if you could tell scientists one thing about curiosity, loss, and persistence, what would it be?
Well, I would just actually quote or paraphrase actually what Einstein said. And Einstein essentially said that imagination is more important than knowledge. Knowledge is limited, but imagination encircles the world. And what he meant by that was not that we don't need knowledge, but it's actually our imagination that gives us the interest and the quest to obtain knowledge. Okay, if we go back even as far as back whatever these first human beings did when they saw lightning creating fire, their imagination was sparked. And their imagination is what led them to be able to do it themselves. And it's our imagination that put us into space. It's our imagination. I mean, if you look at the people who were early scientists who were interested in space travel, they were motivated by people like Jules Verne. And a lot of engineers and things like that, even in the space program, Star Trek. was what stimulated a lot of them to go into it. So it's our imagination. As human beings, it's our imagination which gives us. So to me and to young people, I would say, use your imagination. Whatever you imagine, what we don't even think about sometimes is even the most ordinary level. The place that you live in, that was someone's imagination, okay? And it was created. We live in a world that was imagined. So you should use your imagination to try to make a difference, a positive difference in this world.
That is tremendously beautiful. Thank you so much. That's really powerful and motivating. It's almost like endless energy.
Thank you. Well, it's been a pleasure for me.
Well, yes, Dr. Mallett, thank you very much. I genuinely appreciate it and for answering my questions and for writing your phenomenal book. Thank you for your time. It's
Oh,
going to be a treat for my listeners. It really is.
thank you very much.
Dr. Ronald Mallett's story is more than a tale of equations and theory. It is a testament to the power of human perseverance. What began as a child's wish to see his father again became a lifelong pursuit that bridged the emotional and the mathematical, transforming loss into a legacy. His work reminds us that science often begins not with cold calculation, but with love, longing, and the courage to imagine beyond accepted limits. Through his determination to explore the deepest structure of space-time, Dr. Mallett shows us that curiosity can heal, that imagination can endure, and that even grief can become a force for discovery, bending not only time, but the very shape of human possibility. Thank you for listening to Math, Science, History. And until next time, carpe diem. Thank you for listening to Math, Science, History. If you enjoyed today's episode, please leave a rating and a review because those ratings and reviews really help the podcast. If you would like to listen to Math, Science, History without the ads on your podcast player, visit us at mathsciencehistory.supercast.com. There, you can sign up for a tier, which will give you early release podcasts, research notes, bonus material, and discounts on our merchandise. Also, you can find the transcripts at mathsciencehistory.com under the link called Transcriptorium. And while you're there, remember to click on that coffee button and make a donation because every single dollar that you donate supports our production costs and keeps our educational website free. And until next time, carpe diem.